In this video, I'm going to be talking about how to solve a two-dimensional collision problem using the conservation of momentum, which is basically summing up the momentum, which is m times v of all the objects before the collision, and that equals the mass times velocity of all the objects after the collision. Now, if it's in two dimensions, which this one is, which basically means that there's some vertical and horizontal movement in it, or some sort of angles, you want to make sure that you break stuff into an x and y component, as you see here. So it's the same principle of this momentum before the collision equals the momentum after the collision, except we're going to break it up and look at it in two different components, the horizontal component and the vertical component. So if you take a look at our scenario, we have two masses, m1 and m2, which are both the same unknown mass. And m2 was initially here, it was at rest, and m1 moved in at 5 meters per second, struck m2, and now both of them are moving off at different angles. So what we're going to do is solve for the velocity for m1 and m2 after the collision. This is a pretty tough problem because it looks like there's a lot of unknown variables here. So we really need to know our concepts well. We need to make sure we stay organized, set up everything, and see how to solve, see what we can do to solve for our two velocities. So I'm going to go ahead and call this one VF1, and I'm going to go ahead and call this one VF2. And then each of them have a horizontal component. I'm going to make sure they don't overlap each other, so I recognize that there are two different velocity vectors there. If I lay them on top of each other, I might forget and only use one of them. And then we know that there are also two vertical components too. Okay, so things I want to keep in mind is as I'm taking a look at all these vectors, I don't care too much about these red ones at this point. Those are my final solutions that I'm looking for. But as of now, I'm just going to focus on the orange one and the green one. I could tell that this green one is upwards, so I am going to call this one positive. This green one is downwards. It's definitely going to be negative. And then I have two orange vectors pointing to the right. Those are both in the positive direction, the same direction as this object was moving initially. So I'll say everything to the right is positive, everything to the left is negative, which there is nothing to the left. Everything up is positive and everything down is negative. All right, so based on that, I'm going to go ahead and set up everything I know in my X column and my Y column and see where that brings us. Okay, so I set up everything I knew and I almost forgot this negative over here, so I had to correct myself and make sure I subtracted these two Y components. Okay, so speaking of the Y components, initially, if this one's moving to the right and then my M2 was here at rest, we have nothing moving in the upwards or downwards direction. So we'll say that there is no momentum in the vertical direction overall. Afterwards, we do have some upward movement. So we broke those into these two green components. And if you're wondering how I got the two green components, it is mass times velocity. I just use a generic M because my M1 and M2 are the same unknown variables. So I did M times my V. If you're wondering how I got my V, there's some steps that I put over here so you can see how I did the trig. And I made sure I subtracted the two because one is up and one is down. As I said, I almost forgot that, but that's a crucial part to solving the problem correctly. In the x direction, we have the m1 moving along, so that's just m times 5. And then afterwards, it's these two orange vectors combined. So it's mass times the x component of my 30-degree triangle, and then plus mass times the x component of my 45-degree triangle. Again, you can review this part over here if you want to see the steps to solving for the x component using cosine. Now, I have a lot of unknown variables. One thing I can do that I definitely want to is my masses all drop out. So that actually works out nicely because we have the same m's here, and then we just have a 0 and two m's over here. So your m's actually drop out, which makes things pretty nice. And so far, I have two unknown variables. As of now, it looks a little intimidating because I have some cosine and sine functions, but remember, those are just numbers once you place them into a calculator. So anytime you have two unknown variables and you have two different equations, you're going to use a system of equations. So what I can do is rearrange one of the equations and solve for a VF1 or VF2 in terms of the other one. Okay, it really doesn't matter which one you use. To me, this one just looks like it's going to work out a little bit nicer just because there's a 0 here. So I'm going to go ahead and solve for VF2 in terms of VF1 on this side.
Avant, tu voyais que de la merde. Maintenant, au moins, tu vois plus rien.
All right, so what I did was I took this entire part, and since it's VF1 sine 30 minus this whole section, I added it to both sides, which basically just sent it over to the other side. And now they're equal to each other. I divided both sides by sine of 45. And then I just kind of divided these out just to simplify the look of it. Technically, if you want to be a little bit more exact, you can leave these as is. But this gave me a coefficient of 0.707. So VF2 equals 0.707 VF1. Okay, so as I said, I wanted to do a system of equations so that I can solve for what I need. And what I can do is over here, I have a VF2, and I can substitute this in because VF2 equals 0.707 VF1. So I'm going to go ahead and sub this in over here and then see if I can solve for one of my unknown variables.
Avant, tu voyais que de la merde. Maintenant, au moins, tu vois plus rien.
All right, so what I did is I just rearranged things a little bit because when I have a coefficient, I like to put it in front of the variable. So I took this cosine of 30 and just scooted it to the front over here. And then I took this cosine of 45 and scooted up over here. And then I replaced that VF2 with my 0.707 VF1 right here. Okay, so at this point, I took my cosine of 45 and multiplied it by 0.707. And then I took my cosine of 30, and then I added these two coefficients together because they're like terms, and that gave me 5 equals 1.37 VF1. So I can go ahead and divide both sides by 1.37. And then my VF1 comes out to 3.65 meters per second. Okay, and then now if I want my VF2, I can pretty easily solve for that. Okay, so let's go ahead and sum up our steps. The first thing is to make sure you have a nice drawing, especially just creating some triangles, doing some labels. I just do some labels to remind myself which ones are positive and negative, because that's going to have a big impact on your answer. You're going to use some trig for those different components, typically sine for the y component and cosine for the x component. Not 100% of the time, but usually you will. So I set up all of the momenta before and after the collision in the x direction and the y direction. Turned out that because I had two unknown masses that were the same, they dropped out. And then I just left things in terms of VF1 and VF2. So anytime you have two unknown variables and two formulas or two equations set up, you can use a system of equations. It doesn't matter which one of these equations you used, and it doesn't really matter which one you solve for, if you solve for VF1 or VF2. The point is you just want to use one of them and then solve for one of the variables in terms of the other one. Okay, as I said, I picked this side over here. It looked a little easier because it had a zero, so I thought it would work out a little bit more simply. But it really doesn't matter in the end. If you do your algebra carefully, you're going to get the same solution either way. So I came up with my VF2 in terms of VF1. So later on, I can find my VF2 in the other equation and substitute that out for the new 0.707 VF1. Now everything is in terms of VF1. So then you can solve for one unknown variable, and then in turn afterwards, you can solve for the second unknown variable. So I hope that was helpful in helping you set up, understand, and solve a 2D collision problem with two unknown equal masses and two unknown final velocities off an angle. Thank you very much for watching and listening.